if you're still not convinced, we can refer back to this table. In this table, it summarizes the initial concentration of the reaction for N2O4 to be converted into NO2. And you can see that in all experiments, even though the initial concentrations might be different, okay, they might be different over here, in the end, at the equilibrium, the Kc value all ends up to be the same, because all the experiments are conducted at the same temperature. So even if you start out with different concentration, the equilibrium is going to adjust itself so that the Kc remains a constant no matter what. For the final part of this lecture, let us go on to calculations on the equilibrium constant. Example 1. At the equilibrium at 490 degrees Celsius, the concentration of iodine is 8.62 times 10 to the power minus 4 moles per dm cube. The concentration of hydrogen is 2.63 times 10 to the power minus 3 moles per dm cube. And the concentration of Hi is 1.02 times 10 to the power minus 2 moles per dm cube. And you are supposed to calculate the Kc for this equilibrium reaction, in which all the reactants and all the products are in gaseous state at this temperature. So you can very easily write the Kc expression, the concentration of Hi raised to the power of 2 over the product of the concentration of H2 and I2. You substitute the value into the equation and you get 45.9 as the value for Kc for this reaction. Is there any units for this Kc? If you are sharp enough, you have realized that there are no units for this Kc value. Okay, because at the numerator, the units are mole per dm cube. At the denominator, at the numerator is mole square dm minus 6. At the denominator is also mole square dm minus 6. So the units cancel out, so there are no units to this Kc value. Example 2, the reaction 2D plus E to give you F was allowed to reach equilibrium. The initial amounts of the reactants present in 3 dm cube solution were 3 moles of D and 2.25 moles of E. At equilibrium, there were 0.60 mole of F. Calculate Kc. For this kind of calculations, I want to introduce you all to the ICE table. Okay, the ICE table over here, ICE. Okay, in which we take the first letter of these words, the initial number of moles, the change, either in terms of loss or gain, and the equilibrium number of moles. Okay, and we call it an ICE box. Okay, let us look at the ICE box and see how we can solve this problem. We want to fill up the table. So we have initial number of moles. We started out with 3 moles of D and 2.25 moles of E. At the start of the reaction, there wasn't any F, so we put it as 0. Now we know that at equilibrium, the number of moles of F is 0.60. Now obviously, F would have changed. There would have been a gain of F from 0 to 0.60, and that change is positive 0.60. Now if you look at the mole ratio, how do we get 0.60 moles of F? That would mean that 0.60 mole of E would have reacted, and minus 1.20 moles of D will have reacted, because the mole ratio of D is to E is to F is 2 is to 1 is to 1. So we can do a simple subtraction now. 3.00 minus 1.20 to give you 1.80, and 2.25 minus 0.60 to give you 1.65. This would give us the number of moles at equilibrium for the entire reaction. Not to forget, in the calculation of Kc, we are not considering the number of moles, but we are considering concentration. So the entire reaction vessel is a 3 dm cube vessel. So we need to divide the number of moles by 3 to get the equilibrium concentration in terms of mole per dm cube. Now that you have the equilibrium concentration for the reactants and the products, it will be easy for us to calculate the Kc value. The Kc expression would be the concentration of F as the numerator, and the concentration of E multiplied by the concentration of D raised to the appropriate power as the denominator. Okay, and if you substitute all the values inside, you should be getting a value of 1.01, and the units of this Kc value is mole to the power minus 2 and dm6. Example 3, let us consider the Haber process. Nitrogen reacting with hydrogen to give you ammonia gas. Okay, initially, we have 1 mole of nitrogen gas and 3 moles of hydrogen gas. At equilibrium, we have 0.500 moles of ammonia gas present. And the total pressure of the system is 10 atmospheric pressure. Now you're to find the value of Kp. Okay, we draw up the ice table again. Initial number of moles of N2 is 1 mole, 1.00 moles. Initial number of moles of H2 is 3.00. We started out with nothing. No ammonia gas was present in the system initially. Okay, but at the end, you know that the equilibrium number of ammonia is 0.50. So from 0 to 0.50, this would mean that there is a gain of positive 0.50 mole of ammonia. Now by mole ratio again, okay, 0.50 is actually 2 times of 0.25. Okay, because if you look carefully at the equation, the compound, okay, or the molecule with the smallest molar ratio is actually N2. Okay, and that would mean that 0.25 moles of nitrogen will have reacted, followed by 3 times of minus 0.25 of hydrogen that reacted. And if you do initial number of moles minus the change, okay, minus or plus the change, it will give you the equilibrium number of moles for nitrogen and hydrogen and ammonia. Now at the equilibrium, the number of moles of N2 is 0.75 moles, and the number of moles of H2 is 2.25 moles, and the number of moles of NH3 is 0.50 moles. So the total number of moles would be the addition of these 3 numbers to give you 3.50 moles.